Okay, last question of the paper. Let's see what's been asked. It says the frame of the box indicated in the diagram is made up of 12 plastic rods that have a total length of p centimeters. So it's basically saying if you were to line up all those rods next to each other, the length of those rods would be p. The width of the box is half the length, which we can see because it says the length is 2x, width is x, right? So there's a relationship there. If the volume is a maximum, when you see this word maximum or minimum, you are thinking derivative. Okay, that's what you're thinking. You're thinking I need to get my derivative because that maximizes or minimizes. It then says determine the length of the box in terms of p, show all you're working out. Firstly, let's write what p is. So do you agree with me that there's 4 heights? Look there, 1, 2, 3, 4. So we have 4h, right? Then we also have 4 widths because we have 1, 2, 3, 4. Then we have 4 lengths, 1, 2, 3, 4, plus 4 times 2x. So we have 4h plus 4x plus 8x, which is 4h plus 12x. That's the length. Okay, that's all great. Right, so that's that. But my volume is going to be h times x times 2x, which is effectively 2x squared h. Now we know that this is the volume that we're maximizing, but it's a bit tricky now because now we have 2 variables and we'd preferably like to have them in terms of 1 variable. So, and we know that what it's asked us to get is it's asked us to get the length, right, of the box in terms of p. So now we can't do this and find the length, right? If we have it in terms of h, there's no p in there at all, so we're not even answering our question. So let's try and get rid of that h, because it hasn't asked us to give it in terms of h, it says in terms of p. Let's try and make that h in terms of p by using this equation over here. So I'm going to say p minus 12x equals 4h, therefore h equals p minus 12x over 4. Right. So that's what h is. Let's sub it in here. Right, and then we now have an equation in terms of p and x, which is what we want. Let's just times it out, because before we get the derivative, which we need to in order to maximize, we want to get individual terms. So I'm going to get a 2x squared p over 4 minus 24x squared over, x cubed over 4. Simplify that, right, and that's that. So this is all still my volume. So now I have my volume, I have it in terms of x and p, fantastic, but I'm going to get the derivative in terms of x, right, because x is what I'm looking at the length is in terms of x, but we want to do it in terms of p. So we're going to get the derivative, so do the shortcut there, so it becomes x to the p minus 18x squared. We set this equal to 0 because that's what we do when we get a maximum, right? Because basically when we're getting a maximum, we're saying we know that it can be drawn, in this case, a parabola, right? And we know that its maximum point there is going to be the point at which we are looking, right? And that would equal to 0 because the gradient at that point is equal to 0. That's what a derivative is. So we have this, and we want to solve for x in terms of p. Factorize out a x, and then we can see x either equals 0 or x equals, let me get this right, p over 18, right? But it talks about length. Remember, length is 2x, not just x. So what we've done here is we've done this actually for width, which is half of length. So therefore, right, length then equals 2 times this, which is just p over 9, right, centimeters. How do I know it's centimeters? It does say here specifically it's in centimeters, so to be as accurate as possible, please write it in centimeters, and that is the length that you would need in order to maximize your volume of the shape. Okay, so this actually wasn't too difficult, as long as you remember that when I'm talking about maximal minimum, I'm wanting my derivative. If they want it in terms of p, then you have to make sure that you introduce a p there and get rid of other variables that they haven't asked you to write the answer in terms of. Okay, I hope that was helpful. End of paper 1. Well done.